So if you guys could figure out what your paper is gonna be and let me know, like, on Thursday, that would be good. And then I can start getting getting schedules organized, so like which ones go together. And then Tuesday we'll do the midterm, and it's gonna be in class, take up the whole time, and it's based around the paper. So it's not like you have to memorize a lot of stuff. It's more, so it's like, here's paper, here's a bunch of questions, I'm asking you about paper. Some of it you can figure out from the paper, some of it you have to kind of put two and two together, you know, based on global big picture knowledge, not like little detail stuff, right? So don't be sweating it on that end. All right, and so we'll do that Tuesday, and then the next Thursday we'll talk about how to make all the products, and then after that we probably will start in on paper. Now the papers can be deceptive in terms of how much information they hold. But this one we're going to talk about today is packed, and it's only a page and a half, right? So kind of think it through, is it appropriate for what your job is? But if you're a graduate student, if you have, it would be good to kind of have like a bigger topic type thing, but that's why we talk about review articles, but you know, some major publications kind of cover that as well, so bear that in mind. All right, so the one we're going to talk about today, all right, so this got published last Wednesday, and it started hitting my newsfeed Thursday morning, and it's just been all over everything. I'll have TV, I don't watch TV, I stream anything I want to watch, so I have no idea if there's like what kind of coverage this has gotten, like on the news, but it's certainly just like, it hit all my feed, so. All right, this is game-changing paper too, so we'll talk about that at the end. It is intense, and it is like the perfect timing for, you know, like considering exactly where we are, the timing could not be better. All right, so as the title says, they're making them in the UCs, right? And so before we talk about what they did, I wanted to point out a couple of things here, which is sort of handy when you're looking at papers. Look at all those authors on there, right? There's a ton of people. And then look at the institutions where they're coming from. And that helps you kind of start reading a little bit through the line. This is a bioengineering project, you know, for Exelon. And so we've got people from Quantitative Biosciences at Berkeley, Biosystems Engineering in Switzerland, right? And Biological Systems Engineering at Berkeley, Chemistry and Biomolecular Engineering at Berkeley, Regular Bioengineering at Berkeley. Okay, Industrial Biotech, Ministry of Education in China, right? And then Chemistry Department at Berkeley, Plant and Microbial Biology, Berkeley, Biotech, where is it? Biotech at Columbia, National Lab. Okay, Novo Nordisk in Denmark. These guys make yeast. And they're like one of the world's leading yeast people, and they grow very specific strains for customers. So all the major brewers around the world have their own little strains that they have tailored and customized to themselves based on fermentation byproducts and stuff like that. So they're a big party here. Okay, biochemistry, more biochemistry people, China. Now we get the present addresses. Okay, we're now working at Demetrix in California, Berkeley Brewing Science in Berkeley, right, and Genomatica in San Diego. So then you go Google up those companies and you find out all what they're doing and how, like, stuff like this then gets transformed into business type venture. But it also gives you ideas like on these international, like collaborative projects, ideas about where things are moving in different countries. So super interesting. All right. All right, so this is, so we're gonna unpack this paper because it's like, it has a lot of info in it. So, this is from their intro. I mean, they do like this whole little chit chat just about cannabinoids, but so like, this is the major part. Okay, so what they did, they got, CBGA, THCA, now, CBD, they really didn't mention CBD that much in the paper at all. And then the varanic acid, those are the C3 analog at the tail, the C5 is the normal tail. Right? So the C3 tails have different names. And they use the Saccharomyces cerevisiae, which is like your basic yeast, it's brewer's yeast. And they fed it, so they're going to feed it a variety of different things, but, the lactose, just like simple sugar to get it going. And so this is the level of engineering they did. They basically figured out how to engineer the MET pathway, right? And to get the GPP. And they also figured out how to engineer the hexanyl-CoA pathway to get the levottoic acid. Then they engineered the next pathway to this like alleviate geranyl transferase. They engineered the pathway for the two to come together to make the cannabinoids. Right? So they did the whole thing that we've been talking about. They did this all from scratch, right? By successively engineering as they went through. And the amount of work that they did for a page and a half paper is a lot, right? So we're going to talk about what they did. Then at the end, which they talk about this last sentence right here. Then at the end, they extrapolated the process to how to bring a lot of new cannabinoids into a system and how rapidly they can diversify. And so we'll talk about that a little bit too. All right. So this is like their main figure, and then we're going to blow this up and talk about it in like little sections. But this is just a schematic of like the whole system that we talked about, right? You've got the hexanyl-CoA to the levottoic acid. You have the whole malevolent pathway to GPP, and then you have GPP reacting with the levottoic acid to make the cannabinoids. And then you make the acid form of the cannabinoids, which can then decarboxylate with temperature and give you your straight up cannabinoids. So it's just your basic scheme that you're used to seeing. All right, so let's look at the close-up part. So what they did first was they so they took the enzymes so these are known enzymes that you can reproduce, right? And so they took the enzymes from the cannabis and stuffed them into the yeast. So then the yeast start working that cycle, right? And the beginning part, they weren't making very much olivetolic acid. They were only making like 0.2 milligrams per liter. Yeah.
So when you say they stuffed them into the yeast, you mean they like transformed the plasmid and that, or did they just inject the enzyme?
No, I think what they do is, a minute. I just reread it this morning.
But they like made it so the yeast made its own enzyme.
No.
Oh.
No. The yeast did not make the enzyme.
Oh.
They do have an experimental section that was in the extra supplement.
I'll check.
So look at that. The thing I got first off was that they weren't like, but that would work to like, I didn't think they were just stuffing the code in to make the enzyme.
I'll check it out.
But they could have, yeah. They have really detailed notes attached to it, so when you download it, it downloads all the extra material as well.
Okay, yeah, I was kind of off topic. I was just curious.
No. But those enzymes are really well characterized, and they have been known for like 20 years. So if the primary sequence is known, you could just like code that in.
Yeah.
So anyway, it wasn't that great, right? So they didn't get a whole ton. So then what they did is they fussed around to optimize it, right? And so this up here, these are just all the different yeast strains that they ended up with because they would treat each one as a different experiment. So they, YCAN01 is the one they started with. That's the one that got the 0.2 milligrams per liter. Then they worked on feeding it like hexanoic acid to try and get that part going, to get more hexanyl CoA going. So they tried that, and that was dramatic improvement. And then they also added in this other enzyme as well as hexanoic acid, and that gave them their best shot. And then this hex PW is like a whole nother enzymatic pathway to make hexanyl CoA. And so which is not in cannabis, it's in other things, and they added that in as well. So they just kind of fussed around with that to like figure out how to optimize getting that piece, right? And I did that. Then the next thing, and this was the most problematic part of the whole study, was to figure out how to make GPP, right? So this is just like a little quote for them, right? So the whole olivetoline geraniol transferase, that has been really well known and it's really well defined, and it got a patent too. And so the problem that they had is they couldn't get it to work. So then they went and looked for enzymes that would make GPP, but they were trying to limit it to ones that would not go on to make a bunch of farnesyl PP. So this makes the sesquiterpenes, this makes the monoterpenes. So regular plants, so like all your herbs and stuff like that, they don't have a stop once you get to GPP, and they just keep moving on, and they make the FPPs, and then they move on and make they just keep that cycle going and make bigger and bigger compounds. So the plants that intersect at the GPP level and have like side shoots, which is the olivotolic acid. So hops are one. So they took two enzymes from hops. So they're called alpha acids or bittering acids. It's a very generic term, but they are the components in hops that are responsible for the bitter taste in beer. But it's a similar process to what happens with the cannabinoids. There's like a diverting pathway and an enzyme involved in that sucks up your GPP. Right? So they got some of that, and then there's like another plant that they got some stuff from, and basically they tried to figure out if any of those would work. So these are all the different ones that they tried. Trying to get one to work. But sure enough, they got one to work. So once they had like the hexanyl CoA, once they had the GPP and the olivotolic acid, then they're off to the races to make cannabinoids, right? So, and we're going to talk about HPLC at the end of this. So this is their HPLC data, right? So this is just their peak, their chromatograms. So this is just their peak for olivotolic acid, and then their peak for production of CBGA, right? So yeah, this one was good. Those were their standards. 10 got plenty of olivotolic acid, but not making any CBGA. So they got that going. So now they're up to 136 milligrams per liter. Doesn't sound like a whole lot, but I bet you recycle and it kind of starts adding up. All right. So then, once they got the CBGA, then they had to convert that to THC. Now, primarily, and CBD. So, okay, so then what they did, so they, they must have done sequencing based on this. They must have done the whole thing with sequencing. Because they inserted that whole sequence for the THC and the CBD enzymes. They inserted that into their yeast sequence. So they did all that sequencing.
So you think that THCAS is like a gene?
No, the AS, that's a synthase.
Oh, okay.
So that's a synthase enzyme, right?
Mm-hmm.
And then the CBD AS is the synthase enzyme to make CBD. So like in the plant, you would have those, right? So then that facilitates then the CBG going to those, right? Because those are acid-catalyzed reactions, so that you have to hold them in place so they have like an aspartic acid proteinating thing. So they're doing the same thing here, but so they put the sequence in, and then they basically are confined, so they did this, and so this tells you like how much they were getting, and let's see, what did they get? 1.1 milligrams THCA, 4.3 micrograms per liter of CBDA, so way more THC than CBD, yeah, 2.3 on the other one, milligrams versus 4.2 micrograms. So in both cases, a lot more THC than CBD. But you could probably figure out how to split that. We're so inclined. And then again, this is their data over here on the right. And so what they noticed when they did this, that they got the 5-carbon tail, which is like regular old CBD and THC, and then they got the 3-carbon tail. So they figured, okay, those enzymes aren't specific enough to direct just getting the regular sized tail, that getting the 3-carbon tail, that comes from the butyl-CoA, that somehow that's all involved in all of the soup as well, right? Even though, like, look at this one, like, so in the CAN 43, you've got lots of the short one and less of the regular one. And the ditto with the THC variant as well. So that's super interesting in terms of how they, how that kind of came out. All right. So then they wanted to fine tune the production of the CBG and the THCA. So they mess around with that. So these are enzymes, and so they added extra copies of the enzyme, right? So especially this one. So they put like the first one in, and then they put a whole another extra one in. So that's these two. And this is that's a very specific one for, that has to do with GPP production. And these are the ones that have to do with obligatory acid production, right? So they did those little combinations, working on that, trying to get that optimized. So they did all that. Not too shabby there. I mean, they're getting up there 7.5 milligrams per liter, right? In terms of this. And then they did the analog one. So this is like cool. So then what they did is they gave that yeast strain, they fed it with 19 different fatty acids. So those would be like hexanoic acid, hexanoic acid, those kinds of things. And they put in tryptophan version, right? And and then they put in a double bond version. So they did just like a whole different levels of the length, branching, and gradient saturation. So they did that and looked at what they got, and then they also looked at, if you fed them all that stuff, then what would you get in terms of like the THC analogs as well, right? So they got this broad sweet thing going, and that is in here. So these are all the variety of different chain lengths that they coded for. And then you've got your substituted obligatory acids, you have your substituted CBGs, and your substituted THCs, all of the acid levels. So what you got is you basically have, for the most part, where you can manipulate that side chain and get all sorts of stuff. So this diversifies the known cannabinoid family, right? And it also allows you to specify what you want if you get ideas based on other types of compounds that have shown pharmaceutical progress with something or other, that you can then go and manipulate what that side chain is. Right? So they did that, so that's pretty cool, and then they're still not done. And then they did post-fermentation modifications on the product mix that they got. And they did this as a proof of concept that this would be something that could be achieved. achievable, it wasn't really part of the end goal. So they had the system set up where they basically, did like this, put this azides on the chain, and then this is gonna complex it right here. Okay. So that was kind of interesting as well, because it's the same thing. If you get this idea about these are structural elements that may be important for something, then now you've got a way to actually go and make all this stuff. Alright, so this is what they did, and this is all what they talked about in their paper, right? So you go read the paper, it's pretty short, but I think there's like some fancy, like the bioengineering part of talking about like the biochem part, which is like, ooh, that's like a little on the technical side, but for the most part, you can figure it out really easily, right? So let's talk about what they didn't talk about and the implications of that too, right? So they did not do any GC work. So they know nothing about what terpenes were along for the ride with this. But they may not be interested in that, or they may not have them. Or they may need to have like a bunch of extra enzymes involved in order to make those once you get to GDP. So there's like some questions about all of that would be a little fuzzy, but those questions could certainly be addressed. And if you do need a bunch of extra stuff to make that stuff happen, then based on this work, it should be relatively easy to add those things in as well, right? In which case, then you could mimic the entire suite of everything you're interested in. You've got all your terpenes and all your cannabinoids. And down the road, you should be able to adjust to get what you want, right? In terms of how you're doing your engineering. So, in terms of like a biochemical synthesis system, this is like super important because it's going to be like the base of how big pharma is going to enter into production for all of this stuff. Big pharma is not going to be growing. They're going to be feeding these bees, right, in giant tanks and stuff like that. So, and the speed, we'll talk about the medical research. It's just scratching the surface right now, barely scratching the surface. So as it moves forward and more of those cannabinoids get looked at, those already like anti-inflammatory is a big one, right? So then you can like rapidly make a whole suite of things and screen them, like for potential good stuff. So you see that happening. But I think it's also a game changer because it confronts the legality issue. So I've been trying to figure that out. Like, okay, so you've got this way now to produce all this stuff. So how does that fit in with how those laws are written and how does that be viewed? Right? Because I haven't heard about that yet, but I'm sure people are talking about it. So this is a lot of text, sorry, but it's just getting it all on one page. So this is the Controlled Substances Act. And so they define each schedule, right? And Schedule 1, so under the definition of Schedule 1, right? No currently accepted medical use. This has been around forever, even though now the Marinol, Dronabinol has exempt status. They're schedule 3, which is the same as Tylenol 2. Right? It's like, okay, like how they figure this out is beyond me. It makes like, it's not logical, but I guess they're not logical. So schedule 1 is, no accepted medical use, that there's no safety information, which is like new, and that there's high potential for abuse. So the stuff that's in schedule 1 is like, so this is how they have it like labeled out. So like heroin, like LSD. Now when they talk about cannabis, I mean they talk about the plant. They're not talking about yeast products, right? So they talk about the plant just the same way they talk about peyote, right? That's like mushrooms. And then they have like a variety of like drugs. All right, and then schedule 2 is just the high potential for abuse, but it has accepted medical values and its safety is known, right? Then you've got schedule 3, they have a potential for abuse, but it's less. How they define less is hard to know, because what you'll notice is it's not on this list. I have another list. It's like all the opioids that are part of the opioid crisis, they're all like way down scheduled. Okay? So then you got these guys, so schedule 2, and then there's schedule 4, so it's just like, as you get into this level, it's like, okay, there are less potential for abuse, and so if they have narcotics in them, so you'll see in this table I have N stands for narcotic. If they have narcotics in it, it's below a certain level, right? That's how you get, and the cough stuff that has like codeine in it. So this is like, stuff that's over the counter, basically. Yeah.
Where does like alcohol fall into this? Because alcohol,
It doesn't.
even though there's like alcoholism and alcoholism, etc.
Yeah, but it's not a scheduled anything. I don't think.
Isn't it the system came about right after Prohibition?
Yeah.
Because the system was designed to crack down basically on the cannabis. Like, basically, this is a system of systemic racism.
Gotcha.
Yeah.
So,
Yeah. And
with modifications.
so,
Yeah.
because cannabis used to be legal.
Right.
Everything used to be legal, basically. And then as time went by, now you can say, okay, well, let's just tax it, legalize and tax, but this is just kind of, So getting it undone is challenging. But it has to do with, so this is why that making it for me could be the challenge, because so much of this is oriented towards the plant, and it's all written as the plant, right? And so this is like how they do those definitions, and then if you can download the list. So there's a list of a 16-page, actually 17 pages now, because I just looked at the update today, but these are exactly the same. So there's a list of all the controlled substances, right? And so these numbers, the 7360 number, that's a DA number, and then you have the schedule number, and then you have whether it's a narcotic or not. So, that just seems kind of weird. And then they have specific exemptions, and you can download the exemption list as well. Although I just did that this morning, because I'm like, I wonder if they've updated it since the Farm Bill. But they haven't, it's basically the same as what it's the same document as what I had before. Dronabinol, and I'm like, on the exemption list is specific delivery systems, like how you purchase it. So this is like in the gelatin capsules, right? So that's how they set it up. So if you work in a lab, you can buy standards that are like in little glass ampules. Those are specifically things that are exempt and have the DEA exception numbers, right? And if you have a license, then you can purchase those items, right? Kind of how it works. So under 7360 is the plant. Marijuana extract doesn't have anything there, right? And there's been some comments, like the stuff goes on the Federal Register and then it's open for comments and then people comment on it. Right now, that is blank. So what does that mean? Right? But if they're defining marijuana as the plant, then the extract would be stuff that comes from the plant. So that's kind of the argument there. But then they have like the tetrahydrocannabinols, and they just have like this vague little list, right? So what are they, how is this around CBD, what's going on here, you know, it's like, talk about vague and fuzzy, right? So I think that, say like on the yeast situation, the only, like that would be the challenge, would be the 7370, right? Because that's the only thing that we talk about is the plant. So I think that could be really super interesting to see how that goes. But that's very cool. All right. So the last thing I wanted to talk about today was how you go about doing the cannabinoid analysis. So this is just like the little flow chart that we were talking about. So this would be the kind of suite of things that you want to look for. So you've got, so for the biggest issue with this type of analysis is that you have the acid forms and then you have the decarboxylated forms, right? And the decarboxylation happens under heat. So that pretty much precludes the use of doing GC. And it would be hard with GC because then you have to get all your terpenes and stuff out. Then you have to ramp it up and like cook it to get the stuff off the column because it's pretty high molecular weight. It's over 300. So it's really dicey in terms of that. So you're definitely going to decarboxylate everything if you're doing it by GC. So there's no way that you can get like the natural ratios anyway from the sample. So the approach is going to be doing it by HPLC. So we'll talk about that. So HPLC is basically taking the concept of color chromatography and turning it into an instrument. So in column chromatography, you basically get a glass column and you pack it with a stationary phase, which is silica gel. And you can buy the silica gel with different coatings on it. So, so we talk about it in terms of like normal or inverse. So that just has to do with the polarity of your packing material. So then you pack up your column, then you load your sample on there, and then you add your solvent, and then you see these bands, as your sample travels down the column, it starts to get separated out in bands. They're not colored, usually they can't tell where they are. And then you collect your fractions, and then all of the fractions that have your bits in that you want, then you wrote it back and down, and then you have your isolated components. So that would be how you do it if you're doing that. So this technique has been around for a long time, and since 1903. So this guy, Mikhail Svet, so he's basically the guy, the Russian guy. He invented column chromatography, and he did it. His experiments were separating the plant pigments, right? And now this is like we do this like in grade school, like with paper chromatography. You can do it with paper toweling, but like you do paper chromatography like on chlorophyll from plants, like with kids, and then they can see like the stuff you do on paper. Or you do it with like magic marker dyes, you know, you see the different colors on that. All right, so that was it. That was all there was, regular old column chromatography forever until 1978, and this guy Clark Still got this idea about pushing the solvent through. And sure enough, you push that solvent through under pressure, you get a better separation. It goes a lot faster and you get better separation, right? So that's flash chromatography, and this is pretty much what everybody does now, right? We don't do the regular old-fashioned anymore. And so to go from here then to HPLC, to make an instrument out of it is not that big of a leap, right? So, so these instruments first came out around that time. So what you have is you have a column up there. It's chip-plate metal, and it's all packed. It's got fittings on it because now we go really high pressure, right? And so we got the column, and then we have to get our sample on there. So here's our sample. So we have to have some either by hand, injection, or auto sampler. We need a pump that can pump our solvents. Right? So we have a variety of mobile phases. So you can start your mobile phase out when you just started out as a blend of solvents and then just pump that through. Or you can have multiple mobile phases and then you can program your pump and program your delivery of the solvent, and that way you can change your percent over time. Right, so that's probably a more common way of doing it now. Right? So then you push everything through the column. It's got to go to some kind of detector, and then you see your kinetogram on the computer screen, and then your solvent, you know, your stuff is actually in that waste. Like there are setups for this that you can use for quantitative collective work, and that would be then you blow it back off with solvent and you keep it good. But you have to have a really high throughput to get enough if you're going to do a separation like that. That's not good. So primarily it's just used for analytical, and then this is a problem, what to do with all this waste. So what a lot of people do now is say, distill it, and then it cycles back, right? The distilled solvent. Depends on what you use. And what's in your sample. All right, so here's a picture of a contemporary one. Right, so you got your solvent. I think we split out. Do we have one like this? No, I think ours are pretty old. Right, we don't have really good ones. But you got your solvents up there. you got your control module that controls like your pump pressure, all of that kind of stuff. And we're gonna look at a couple of different, published methods for cannabinoids, and then you'll see like the kinds of specifications that people have, and the things that you need to keep track of if you're developing methods yourself, right? Injector system, all of this stuff. All right, so what you can mess with is your mobile phase composition and gradient and your flow rate, which is based on your pump setup, how much you inject, right? What kind of packing material you have. Like there's lots of fancy specialized packing materials. Temperature, that's a factor as well. You know, how long you let things go for. And then the biggie is what kind of detectors you have. Standard issue is a diode array detector. So this is just exactly what it says. It's a diode array. It shines light typically throughout the entire UV spectrum, right? And so as long as you have a chromophore in your molecule, you're going to get a signal. So that's like benzene ring, pi bond, carbonyl, you know, it's the classic kind of functionality that you see in biomolecules, right? Typically, you're going to be looking at above 300 molecular weight, if I feel correctly. Right? Lower than that, you're in the volatile region, and you're going to be tending to GC as your technique. This technique requires more babysitting than GC, primarily just due to the fact that your mobile phase is liquid versus mobile phase is being gas. Right? So there's a lot more fiddling around, and there's a lot more stuff that can go wrong. Yeah.
I'm surprised it said degreaser. That is never.
Oh,
seen that.
degassing.
Oh, degasser. I thought degreaser is like.
Oh, no.
No. Okay, never mind. Degassing. Yeah,
no,
that makes
it's
sense.
a degasser. Yeah, so you want to get all the gas out of the solvent, basically. Yeah. Yeah, and so diode array standard issue, or just like a old-fashioned UV disc, those sort of kind of things. But the biggie, and this took a long time to figure out, is how to hook them up to a mass spec, because you have to get rid of the solvent because it would swamp your mass spec signal. So but you want to keep your good, because that's what you want to put on the mass spec. So it took a long time, and that's called thermospray, and that's the thermospray ionization, and that's like the inlet now to the mass spec. So you can get this set up, but it's going to cost you a ton of dough. These are not, like, the actual LC part is pretty cheap. It's the mass spec part that's not cheap, right? So if you're just going to do like a standard analytical type lab, you're going to be looking at a diode array detector for just standard analytical stuff. But if you're a research operation or you're a bigger company, you've got a lot more cash, you're going to get one of those mass specs. So like all that analytical stuff from the paper, that was all done by HPLC mass spec, right? And the mass spec is tricky because they have all those new compounds, right? So they have to figure that out. Like once you start messing with that chain on the cannabinoids, like most of those aren't known. So you'd have to do like some mass spectral interpretation in terms of how are you going to prove it's a compound, and if these are brand new compounds, then you got to isolate and purify and then send them off for extra crystallization. You know, so there's a lot of background work that goes with that.
Does the diode array detector produce like a fingerprint similar to
No. Basically, it allows you to generate just like a chromatogram. Like, so you're just going to get a chromatogram, but it allows you to detect signal at multiple wavelengths simultaneously. Whereas previously, if you use a UV vis, you dial in the wavelength. And so the entire chromatogram is being detected only at that wavelength. Okay? So the DAD is definitely a good enhancement tool for that. All right, and typically, what you get for your chromatogram, so if you look at this one, so this is like a 16-minute one. So you'll notice the difference between these and like juicy ones, or the peaks are a little broader. That's like classic kind of LC. And then you kind of just run a bunch, you get your standards all organized, and then you can like identify the peaks. And what is nice about this is you can look at your ratio of your decarboxylated to the ones that have the carboxylated still on it, and you can quantify all this. Right? So a bunch of people have been working on, before I talk about that, and then you integrate it, just like you do your GC chromatogram in terms of quantitating. You can do it that way. A good method is going to use an internal standard because there's a lot more variability in terms of the actual production of each chromatogram in LC than there is in GC. So even in GC, you're best off if you have an internal standard if you're going to do quantitation. So the internal standard could be, you're going to see one, it could be anything, and then you have like a no calibration, and then you apply that to your numerical analysis that you're doing. Right? Versus if you have, what did you say, external. Internal is you run your standard with every run. External is you just have a calibration curve, and then you compare your stuff outside calibration curve. Not as robust as internal. All right, I'm going to talk about that. It's like, and that's the other thing about GC. It can just decarboxylate when you inject it in the injection port. That's at 300 to 350 degrees centigrade, whereas LC, you're doing all your injections at 100. All right, so those are just a couple of different methods just to give you an idea of what kinds of stuff we do. So, so this one comes from this forensic journal that comes out of Switzerland, and this has been put forth as a method that various centric countries could standardize and agree on as an analytical method. And in Switzerland, it was primarily used because they would bus people at the border, and they'd be like, "Oh, it's hemp. Right? It's hemp." And so they were really trying to come up with a screen for, is it really hemp or is it trafficking, you know? And their definition of hemp was like 1%, had to be less than 1% THC. And they developed this method using samples that they got when they were interacting with people crossing the border. Right? So they have these solvents, so you basically got acetonitrile, you got TDA, triethylamine, so it's like a base type of buffer that's probably going to work on stabilizing that carboxylic acid so that it's CO2 minus and not complexing with the sulfur gel as much. And then you've got your flow rate, and then you've got your gradient, like what percent of each solvent you're going to do. Isocratic means you're just going to keep it constant over time. Got your injection volume. Then your column is really specified out so that you would just go by that if you're a lab trying to reproduce it. And then, your temperature, room temperature, your detector, and what you're depending on for your primary wavelength, right? And, then what's important for all of these analytical methods, especially if they're going to be used in terms of you're the holder of the sample and question, and you have some authority that's going to pass judgment on you, these are kinds of things that are handy to know, is what is the limit of detection for the instrumentation, and what is the limit of quantification for the instrumentation. And it's just like when you go to the doctor's office and they don't tell you that something's zero. Because zero doesn't exist. It'll always say less than blah, 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 because the blah, blah, blah is the limit of detection or the limit of quantification. They never really explain which one it is. But, so they can get down pretty low here in terms of that 0.04% by weight of, back to the, actual sample that they started with, for limited detection. So if you're claiming that your sample's 10 and you're under 1%, it will be very clear whether or not that you're under that 1%. And then that limit of quantification is, it's close. So like if you look at THC as being 0.24, so our current limit for hemp is 0.3, right? So it's kind of right there. But then like the THCA, that limit of quantification is kind of higher than that. So that's a little bit dicey there. Anyway, this is a 2014 method. All right. So that's what it was used for, and they can report like their THC content as the sum of their decarboxylated versus carboxylated, and all of that. So this is the one that the United Nations is working on as trying to socialize across UN countries in terms of using this as a standard. And this is another one from the Pacific paper, which is from 2009. This is older, but the chromatograms in here are gorgeous. So same thing. So they're using methanol, they're using ammonium formate, and they got the flow rate, and they've got, this is a ramp now. So they start out percent of solvent A, percent of solvent B, and then they run it for 20 to 25 minutes, and then they, from 25 to 26 minutes, they do a really fast methanol wash. So like they're running it, they start out, and then they it's like, how do I say, it like loads this on, so it sets up the column, and then they're pushing the methanol through, and then they do a really fast methanol wash again, and then they do the next sample. Right, so you're on your auto sample system. Injection volume, this is a standard column. Waters is like a standard HPLC company, the main one in the US. And they're doing the full spectrum. They're not just localizing on one wavelength, they're doing the whole array. And they're using an internal standard. This Prazocam, which is this, is their internal standard, so that gets added to every sample, and that's in every chromatogram. And this is the standard. So this is a standard where everything is 10% weight to volume, And in terms of the resolution, it's gorgeous. This is like exactly what you aim for. So like the hardest part is right here. So you've got CBD and CBG are potentially co-eluting, but they have it down to the baseline, and THC and THCA potentially co-eluting, but they have it down to baseline. You want, this is your minimum that is acceptable. It's really nice if you have a gap. But you don't want too long of a gap, because if you have a really long gap, then your analyses are really long, and they take too much time, and time is money if you're in a lab, right? You want to churn those samples out. Right? So that is just gorgeous. So that's how you do it. And then, and then in this paper, they also show these chromatograms. So you've got extract from a plant. You can like organize all your stuff. So like in the plant, primarily carboxylated. Oh, that is. Here's your internal standard. Here's your THC. Here is your acid. Here's your acid. Here's your THC. Let's do something. They did something different. Oh, I screwed up. This is the delta H THC and THC right here. And then this is your regular THCA right here. That makes sense. All right. So they got everything separated, and in the plant, you've got that not very much is decarboxylated versus with the carboxyl. Same thing in the resin, which is like post-plant production product, is you've got more decarboxylated, but still a lot less. And you've got all of the guys in there, so all of your sort of major cannabinoids are in there. So pretty good deal. All right, so that's how you do it. So you've got your two primary analytical techniques. You've got GC, that's going to cover your monotropics and your sesquiterpenes, and then you have your LC, which is going to cover your cannabinoids. So taking those two sets of data, okay, we're going to start working with those two sets of data to look at how do you go about identifying variety, and like I'll show you some papers and there's some interesting stuff that's come out. And we also take all that information and then sub it out into like chemotypes, which are how do you organize all the samples of marijuana into similar chemical profiles, right? Because the combination of the GC and the LC together is a profile for that variety. Okay? So we'll talk about that and all what you can do with that. So that's all later. Okay? So Thursday papers, and Thursday we'll talk about a whole bunch of products, and then next Tuesday we'll do tests. I'm working on that. Just like